Νομίζω είμαστε έτοιμοι να ξεκινήσουμε. Καλώς ήρθατε. And I'm going to switch to English right away, since this talk will be delivered in English. So, good afternoon, everybody, to people in the room and also to those watching the talk from distance through Zoom or through the live stream. It is a pleasure to welcome back to the Technical University of Crete and the School of ECE, Fotios Lygerakis, who is a recent graduate of our school. In particular, he received the integrated diploma, the integrated master degree in 2019. And before starting his PhD at the University of Leoben in Austria, he held different positions at the University of Texas at Arlington, also at the National Center for Scientific Research Demokritos in Athens, and finally as a research intern at Toshiba Research Europe in Cambridge, UK, where we also had a very nice collaboration and we authored a couple of papers. His work includes contributions to various aspects, various topics of machine learning, data science, and robotics, particularly representation learning, reinforcement learning for robotic manipulation, healthcare robotics, and dialogue systems. Currently, Fotis is a doctoral student and university assistant at the chair of biophysical systems at the University of Leoben in Leoben, Austria, since March 2022. And he focuses there on the representation and robot learning, employing self-supervised learning methods, both contrastive and non-contrastive, as well as reinforcement learning techniques, specifically targeting manipulation tasks. Now, today, we're going to hear from Fotis about a topic with a title From Sense to Dexterity, Self-Supervised Representation Learning, Visuotactile Fusion, and Robot Learning for Manipulation. So thank you, Fotis, for being here on this hot day of summer, and we're looking forward to listening to your talk. Thank you very much.
Thank you very much for having me here. Thank you for the very extensive introduction in so many words about me. So, hello everyone, my name is Fotis. But before I introduce to you a bit more about myself, I want you to get a step back and imagine a very simple task for humans. Imagine you're like walking down a very busy street and you want to get your wallet from your... What you do is to locate with vision where your backpack is and where the opening is, open it, then create a trajectory with your hand to get it inside your backpack, and then you can feel different things without using your vision. You can feel the rigid notebook that you're having there, you can feel the cold metallic feeling of your keys, and somewhere there you can feel the yielding soft touch of your wallet where you can grasp it, but just enough so you don't squeeze it, but to secure it in your hands and get it out. This is a very simple task for humans. Working together, different sensing modalities, and using them to seamlessly manipulate objects. But this is a big problem for robotics. And through my research, this is something that I want to tackle. Overall, my research goes from sensing to control, where I want to learn good representations of modalities, efficiently fuse them for robot learning algorithms to be able to learn and hopefully manipulate things on the real world. The research questions I want to answer during my PhD, and I have answered at some extent, is how we can learn better representations, how we can efficiently fuse different sensing modalities, we can teach robots to perform tasks with high accuracy and robustly. Small outline of this talk. We're going to have a small introduction, and then we're going to talk about my research. Firstly, I'm going to give you a bit of background of what the team in scientific research Fotios. Then University of Texas at Arlington as a graduate teaching assistant, and then finally in this right a very small alpine University of Leoben, where I'm a doctoral student and a university assistant. Okay, as I told you, my research involves around two with we get raw data from sensors, and with in usual from which you an encoder we can get information. In this case, is the activations of a neural network. So as I said, raw data can be pixels. Here you can see the 3 different channels of a pixel, red, green, blue, different values, which actually don't mean anything because it has a lot of noise, a lot of things that are not important, like the background, depending on what we want to do with this information. And then a representation vector, which is what we actually need, is the squeezed information from this raw data, which is essentially a vector, a very lower dimensional representation of the input. And an encoder could be just usually like what I use is a neural network. So how do we get the representations? There are different ways. We can get them with supervised learning, where you train end-to-end a neural network that consists of an encoder and a classifier. You say that this raw data maps to a dog. At this case, you try to predict from which class is most probable for this raw data. And then just when you have it trained, discard the classifier and use the encoder. Now, the problem with this is that the features that you learn, the representations, are very task-specific. So if you have a classification problem, you learn representations that are learned for this specific task. And can we do better? There are other methods that don't use labels on the data, but and this method is called self-supervised learning, where you use an inherent learning signal from the data. Some examples of these is reconstruction or autoencoding, where after the representation, you just add a decoder network in order to reconstruct what you initially had in the input. And your signal there comes directly from your input, so you try to reconstruct the input, so you don't actually need labels, you just need pictures. Another technique for self-supervised learning is joint embeddings. When you say you have 2 different encoders, or you can also have the same encoder, you give an anchor image, the original image, and you also give a positive sample. You can, for example, perturb a little bit, you can change the color, crop it. It's also the same thing. So the representation that these 2 encoders learn should be similar. You can use contrastive learning for that. You can use regularization techniques or energy-based models. But why bother with self-supervised learning? We bother because we can utilize abundant, unlabeled data, and it can give us representation and task agnostic, so you don't have to train your time for your specific task. And they're also efficient. But first, a bit of background, as I told you. Encoders and variational autoencoders. What an autoencoder is, as we also saw in the previous slides, is a neural network that has a very narrow latent space, and this is where you want to squeeze all the information. You have an input layer, you have an output layer, and you try to reconstruct, this is the loss here, you try to reconstruct the output from the input. So if you're far away, you have a big loss function, your loss function is bigger, and you try to minimize that. And at the end, you're going to use this latent representation, whatever downstream task you want to do, application, information, as input to whatever. Now, the variational encoder is a version of adds a bit of regularization of the latent space. Instead of direct learn the representation, you learn parameter distribution of representations. So in this case, we assume that the distribution is Gaussian. So you learn the mean and standard deviation. More because usually where like high dimensional, you learn the mean vector and covariance matrix, but doesn't really matter here. And difference with the simple encoder is that you add this tail divergence at the end of it, which is the regularization. We'll see in a bit what this tail divergence means. Another technique is contrastive learning for self-supervised representational learning, where essentially you have two similar images, and you say that make these two images similar. And we have two dissimilar images, for example, the original image and the negative image, and you say make this dissimilar. The way that you do it is that I would say are vectors. And they're vectors on a unit sphere. That means that their magnitude is 1. And the only thing that we care about is their angle. So if you see, we have the purple, and this is the vector as it is. And what you want to bring the positive sample closer to anchor vector and the negative sample further away from the anchor sample. And the way to do that is using the influence loss. Essentially, what this formula does is in the numerator, you have the numerator makes the representation similar, and the denominator make your representations dissimilar. So, for example, in this case, ZI and ZJ, you plug them in the numerator, and every negative sample, you plug it in the denominator.
What is SIM in the specific function?
Excuse me?
What is SIM, S-I-M?
It's a similarity function. Usually, we use the cosine similarity, but you can use any similarity function.
So you normalize by the length of it.
Yeah, if you use that, that's why I said we're in the unit sphere, because cosine similarity actually normalizes it.
So you ignore the differences
In the magnitude, yeah. It because you want to ignore it because it creates problems with learning stability. You actually try to squeeze the representation space that you can search for these representations. And a lot of times, if you have a bigger space that is not normalized, your representation space, you have collapsing phenomena. For example, you just learn the trivial solution that everything is just the same. You represent everything the same. So it has been shown by a lot of papers that cosine similarity actually works better, especially when you have images.
The problem is actually, or there must be, if a representation vector is low.
Oh, okay. There might be a problem with cosine similarity, because if you use if it happens and the representation vector has small magnitude, and you scale it to have norm 1, then you basically include error. I mean, if the magnitude is small, then there must be a big error in terms of the angle. And this is something that you would like to ignore. So if you take into account the magnitude, this will handle the problem with error.
I actually try to play with these similarity functions, but I see this collapsing phenomena all the time. Because all these representations come from a network and you have a lot of regularization throughout the layers of the neural network, actually the noise is normalized there, and you don't know what noise is actually, especially for images. And you try actually to model noise too in the representation space, and when you have downstream tasks, then these downstream tasks figures out if what is noise. because for some tasks, you want to also have the background as part of information, but sometimes that's not. So it depends on the task. You want to represent everything efficiently. And at this stage, you don't know what noise is, to be honest. Yeah, and please interrupt me if you have questions because it's a long. Yeah, please.
Okay, another question. Can you go back a couple of slides? The previous one, this one. Okay, the latest page. Oh, hold on. Mm-hmm. Okay. So you start from an input layer, which might be a big image.
Yeah.
So this is the vectorized image in pixels.
It can be vectorized, or if you use CNN, is the actual image. If you use convolutional.
Yeah. Okay. And then you get the red node, which is a value.
It's a vector.
Okay, this is a vector.
Mm-hmm.
So the outputs of each green node is a vector as well, or not? I'm trying to figure out.
It depends what kind of neural network you use. If you use a fully connected neural network, it's actually matrices because these are neurons. The green ones is whatever neural network is. Blue is input and output. It's numerical.
Okay, the top green top left green node
Mm-hmm.
takes as an input the entire image.
Yeah,
and
because it's fully connected.
And gets in the output a vector. Okay, got it.
Yeah.
Okay, but the red one is still is a vector, right?
Yeah. The lower dimensional vector. For example, if you have an image that is 256 by 256, 3-channel.
Which are the features that you want to...
Exactly. This is what we actually want to learn and use later on.
Good, thanks.
Like, so now that we have the background about the basic representational learning methods, let's get back to research. And the research question one that I wanted to answer is how we can learn better representations from VAEs. So as I said, a VAE has the architecture of an encoder and a decoder. And if you see it from a variational inference perspective, the encoder is the posterior distribution of the input X of X given the latent representation is actually a distribution, a Gaussian distribution. Now, a problem, before we talk about the problem, the inherent VAE's problem, let's talk about how we train that. As we said, we have a loss that consists of a reconstruction loss between the input and the output. It's usually the mean square error loss or the binary cross entropy, depending how you model the output. And then you have a weighted KL divergence that comes from the actual loss of the variational autoencoder, which is the negative elbow, evidence lower bound. And the KL divergence is between the posterior, which is actually the encoder, and the prior distribution of your representations Z. Now, the problem with that is that the scale divergence here. That means that if you have a very expressive function approximator, as neural networks are, you can create outputs that look very similar to the image, but they're not dependent on the image. Because that means that the encoder Q becomes invariant to the input. Exactly the set. That means that it will not pay attention to the representation, and the representation therefore is any information from the input. And what about posterior collapse and but not do that? For example, you can play with this data part there and make it smaller or bigger. Actually make a regularization more or less. What we did is to use the elbow surgery equation and split the KL divergence into a mutual information term and the KL of the aggregated prior and the true prior. And in this way, we figure out that minimizing the KL divergence, also this mutual information between the input and the representation is minimized. And this is what we want to avoid. And we wanted to avoid it by deriving a lower bound and maximize it so this mutual information doesn't go to zero. It has been shown that the mutual information between two variables can have a lower bound, like the one that you can see here. It's the log of k. It's k is the number of the bats, of the samples in the bats that you have. And the L and C is the info and C loss that we described before that is used in contrastive learning. So what we did is to add the info and C loss to the original variational autoencoder loss. And with a lot of engineering, we managed to propose a contrastive regularization that has smaller reconstructor error, which is exactly what we wanted to avoid posterior collapse, more truthful images being created. And that's work that we presented at the ECE 2023. And from there, as we said, we have the original elbow, we have the elbow surgery that we use for VAE, and then we their dissection of this KL divergence to the approximate here. Because to compute this KL divergence there, we need to do Monte Carlo sampling on other sampling techniques because we don't have an analytical solution for this one. So we showed that we can split this one into an entropy and a cross entropy term. And the entropy term gives you the randomness of the model's latent distribution that you want. And the cross entropy gives you the aligned distribution. Our hope is that we'll have enhanced control of the latent space and have this also give us access to more flexible prior incorporation to that by splitting that into two different cross entropy. That's a work in progress. Still trying to make it work. Because having too many loss functions going against each other is a bit unstable, actually, and I'm trying to incorporate these loss functions in the network itself by different regularizing techniques.
Okay, let's figure out what the last
is the cross entropy between the Q function and Q, the approximate prior of the representation and the true.
Okay, you have four terms. The second term is the mutual information of X and Z, right?
Yeah.
So X is the input and Z is the
representation.
And then you have the entropy of the representation variable and the joint entropy of the representation variable and the representation variable according to its prior.
Yeah.
Okay. And the first term is the
reconstruction error.
It's an entropy as well, right? Or
Yeah, but it boils down for images that it's the mean square error.
Okay. I'm trying to understand what is the connection between these four terms. I mean,
there's no connection actually. It's like evidence lower bound. I have a paper archive on that. It's quite big derivations.
So the idea is to minimize this cost function, the first one, the original elbow, and to minimize it, you want to maximize the distance between the maximize the distance between the prior distribution of the representation and the actual
prior, the representation.
You want
to
maximize this.
You want to maximize this, and you want to maximize the cross entropy. You want to minimize the entropy. You want to maximize the mutual information, and you want to minimize the reconstruction error.
And you do this because you want to avoid the case where the two distributions become equal. P and
No, no, no.
Q?
Yeah, sorry about that. The entropy decomposed VA loss is to actually have better flexibility for the prior. So usually you those prior analytical form,
Okay.
but not everything is as a Gaussian prior, and you can inject your own. You can learn the prior, or you can actually inject that you have for the prior.
Okay, this is about P, the prior.
Yeah, the prior of the latent representation. Because the other, you can have the empirical distribution of your data. You don't have actual access to the latent representation. That's why we do the presentation learning.
Okay, and the only difference between the first and the second equation is that you split the Kullback library distance between into visual information and. So you added actually the visual information, right? Oh no, you have the unconditional. Okay, got it. What was your contribution here? Not the original, right? I mean, the surgery is your part, or
The surgery is mentioned it here.
okay. Okay. Thanks.
Okay, so we have the research question: how can we learn better representation from VAEs? And the research answer to that is the contrastive regularized variational autoencoders. Works. You can feel where the object is and get information about its dynamic. As more Visuotactile fusion. Well, we want to utilize abundant and unlabeled data on representations that are robust. In my opinion. Passive learning, as we said, similar and representations of similar representations of Visuotactile is image and from touch to vision. And altogether, we compose our loss function. Influence that we use for contrast. And yeah. Will be like this. And for intramotor is from vision to touch. Now it's you, but here we pre-train in two different data sets, our encoders, we froze them, and then we test them on different tasks. Our data set also vision-based. And we compared our method with other self-supervised learning methods and with supervised, directly supervised method, so that these representations had access to the task signal, loss signal. And with blue is our method, and it's important to notice here that our method not only outperforms other state-of-the-art contrastive learning methods, but sometimes also outperforms the supervised learning method. That means that the representations that we learn are really good and very informative of the input. The task that we try is a classification of different objects, classification for hardness or texture. And we also show that using vision and touch is better than using only touch. You can see that we measured the accuracy here for the task. We also tried on a robotic data set, a robotic grasping data set from which we had labels for if the grasping was successful or not. And in this case, we didn't manage to outperform the supervised method, which is not common. Like supervised learning should outperform the self-supervised learning. But we managed to outperform other state-of-the-art. Now, the problem was, and we talked about with the team that actually created this data set, was that it was not big enough and not diverse enough. For contrastive learning to work, you need to have big and diverse data sets so your algorithm learns the variation within the data set. So, research question 2 was how we can efficiently fuse different sensing modalities, and the recent answer is MDTAC, at least for now. Maybe we have more answers later on. So that was everything about perception, and moving to control. We implemented Visuotactile fusion for model-free Visuotactile reinforcement learning. Now here the question was, how can we teach robots to perform tasks with high accuracy and robustly? What we proposed is multimodal contrastive unsupervised reinforcement learning, or M2CURL for short, where we essentially use the pipeline we built for MDTAC, where we're using the two modalities, and we augmented reinforcement learning algorithms like soft actor critiquing and PPO, and we combined these two losses to create the M2CURL loss. This is a work that we presented last June in Ubiquitous Robotics Conference, and we're glad enough to get the Best Student Paper Award for this one. Now we test our algorithm for different tasks, including object push, edge follow. I'm going to see in the next slide how they look like. And here less is better because the reward signal was very sparse, and you get -1 for every time that you don't achieve your goal. So the smaller it is, that means the faster that it learns, the faster it solves its task, object push or edge follow. Again, we see that our method outperformed the other state-of-the-art self-supervised learning techniques. And on the top of that, you see the algorithm, in this case, soft-actor critic, having access to the actual state. So where the object is, where the arm is, everything. And you see that with blue, our method has comparable performance, or sometimes actually it outperforms. It's also important to notice that our representational learning technique makes the reinforcement learning algorithms sample efficient. With 100 to 100,000 steps, this is the cumulative reward for 100,000 steps, and we see that it can solve the task even from early. It can do better later on, but and still 500,000 time steps, it's also too few for reinforcement learning algorithms. And this is how the two tasks that I presented to you look like. We have the object tools where you have random trajectory generated, and then you have to follow it. And this is essentially what the algorithm sees. On the left, you have the RGB image, and on the right, you have the... So the third research question I posed was how we can teach robots to perform tasks with high accuracy and robustly. And the answer to that, our answer to that is M2CURL. But what are next steps? And this is the most important thing for me from now on. There are a lot of problems that have not been solved, and I'm looking forward to dive into. First, for perception, is that we need to also use temporal information when fusing Visuotactile fusion. And for robot learning, we have the problem of sim-to-real transfer that we want to do on temporal. We want to pivot towards real-world imitational learning, and I'm going to explain why. And my most ambitious plan is to create a Visuotactile foundation model. But first step, sim-to-real on empty curl. The problem with simulated environments is that they often fail to capture the complexity of real-world tactile scenarios. And that's not quite true because they always fail to capture the complexity of real world. And you can see when you run from the simulated data, how they look like, and what the real data looks on the real robot setup. And the result is that we have discrepancies between simulated training and real-world application. And the way to fix it is performing domain adaptation. And we will do that by training an encoder with self-supervised learning to represent the same way simulated and real data. So at the end of the day, the algorithm that makes decisions sees exactly the same thing, even if it comes from simulation or the real world. Another problem that we have to face is that there is no good simulation for tactile sensing. We have a lot of things that are deformable. It's really hard to simulate these things and be applicable to the real world. So we're pivoting towards behavior cloning and offline reinforcement learning. You can see the setup that we have in our lab. We have a panda arm equipped with 2 tactile sensors and the UR3 with a 2-finger adaptive finger. And a week before, we received the compartments for the lead hand, and when I go back to Austria, I'm going to start building it. So we have also multiple gear grippers and collect data from them. Important part would be the multiple data collection. We're going to use OpenTeach from Indo's lab, which is a very nice framework that you can install on a MetaQuest. And it tracks your hands, and then you can elaborate either, in this case, I'm using the simulated environment of an Allegro hand that tries to pull the cube. But you can also it's also extendable to real robots, and you can teleoperate robots using this framework. And the last thing that I found out there is a research gap is a Visuotactile foundation model. The reason that this gap exists is the lack of diverse and high-quality data sets, and not good simulations, and there's no consistent use of tactile sensors because there are vision-based sensors, force-based sensors, and its directionals has different implementations of the sensors, so it's really diverse data. And the foundation models for vision motor control just started to emerge, so there is no best practice yet on how to go there. There are a lot of limitations for every method that I mentioned, and part of my research is to actually tackle these problems. For behavior cloning, it mimics observed behaviors. That means there is no adaptation. It fails for long-term horizons, and you need really expert demos. Then you can use offline reinforcement learning that you can use any human data because you have the reward signal. So even if it's a bad example, you know that it's a bad example. But then humans are not Markovian. So if you try to solve a problem that has a prerequisite that you're solving a Markovian problem, and your data is not Markovian, then it's still a problem. You have variance across humans, so you have different distribution modalities that if you just use mean square error, you're going to average them. So you will learn nothing. And yeah, the data set size doesn't have enough exploration. And a lot of practical things I'm not going to go through. So to sum up, my research goes around sensing and control, from representational learning to multimodal fusion, robot learning to real-world applications. Beyond my PhD, supervising master theses, successfully 2 of them so far, and I'm also working with another student. I created the Neural Coffee, which is a reading group about research papers on neural networks. In general, I'm writing articles on Medium. I have a few lectures on deep representational learning and tutorials on YouTube of our lab. My most favorite one, every year we're creating a Christmas video with robots in the lab. And if that sounds cool to you, feel free to reach me or anybody in our lab, especially if you want to work with me. These are the topics that we could work together as a thesis, an internship, or collaboration, from self-supervised learning to robotic interfaces. Thank you very much. If you have any questions, I'll be more than happy to answer them.
Thank you, Foti. Very nice talk and very interesting. So let's see if we have any questions. We have a few people attending online. I see Professor Christopoulos there, and there were a few others who disappeared. But so, Professor Christopoulos, if you have any questions, you have priority since you're away. But
no, Mihaly, thank you. I don't have any questions. Actually, there were a lot of problems with the sound, and so I was not able to fully follow the presentation. But I did definitely like the subject matter and what I could see from the slides, even though I was not able to follow most of the audio.
okay, I figured out that something was going wrong with the sound. That's why I added this microphone here. But anyway,
I'm really sorry. I don't know. Maybe it was too far away. I'm really sorry.
I'm not sure the problem was yours. I can also barely hear Professor Lygerakis, and also sometimes there was no sound at all. So I don't know if it's my system or something else. But yeah, thank you for giving us this presentation. It seems very interesting. I like the stuff that you're working on, and maybe we can discuss it. I would have been there today, but I have COVID, so I have to be at home.
I hope you get well soon.
yeah, best wishes for recovery soon.
Thank you.
Yeah. Great. So any other questions from the audience? Yes, please.
Thank you very much for your presentation. Question from me would be, you mentioned that there's a gap between simulation and real experimentation. So could you tell us a bit more about that? Was your research mostly simulation-based? Was it experimental, both?
Yeah, so far the empty curl was only on simulation, was testing only on simulation. And now we want to try to see how it performs on the real robots, and also try to merge that gap that probably we'll have on the real robots. Now, the tasks that we used are not that hard. That means that it's quite easy to interpolate between the simulated data and the actual data, because the tactile information that you get is very, very coarse. Like if you're line following, you just need to learn an edge, where, if you're on the edge or not on the edge. So the task that the algorithms need to solve, it's really easy. If we manage to do that at the first place with a simple task, then we want to move towards more complex tasks, where you actually need to learn to detect textures, slippage, and other things that are important for more complex tasks. And then we're going to have a problem, especially with the simulators that are out there. That's why I want to move more towards simultaneous learning from real-world data, where you have directly data from the actual sensors that you're using, the robot and everything, the camera, the lighting. So you don't have to train first on the simulation and then try to transfer it.
Thank you and congratulations.
Okay, any other question? Professor Lygerakis? Okay, great. I was wondering, Foti, trying to see the connection between robot learning and representation learning. Is the latent space what you utilize for robot learning, since you have a low-dimensional representation?
This is reinforcement learning algorithms are notoriously bad at converging. They need a lot of samples. And the more noise and the more irrelevant noise and the more uncompressed data that you have in the input, the more it's going to take to convert your reinforcement learning algorithm. You cannot give access directly to pixels because it will never converge. So even if you don't use self-supervised learning, you will use some kind of encoder to squeeze this information, and you're going to learn them through a very sparse reward signal, which is very inefficient too, and the representations are not very good in quality. So what we try to do is to pre-train on experiences that these or other robots have, or even data sets, and then use these encoders, either fixed or fine-tune them with the reinforcement learning algorithm, which, as we showed, gives really good sample-efficient characteristics.
Mm-hmm. That was what worked also in our dialogue system. So that's a very key observation, that reinforcement algorithms really want a low-dimensional...
Yeah, we were using LSPI, and LSPI is not based on neural networks, so it doesn't have the capacity of learning these good representations linear. Mm-hmm. So having non-linear representations actually encapsulates all the complexity that you needed. And then if you have good representations, you don't need something very expressive. You just need a good algorithm and a simple, and you can solve pretty much all the tasks.
Mm-hmm. And you mentioned that to learn good latent representations, it's better to use real data compared to simulated data. I missed that part because of the differences between simulation and the real world.
Yeah, if you learn your presentations only on simulated data, it will not capture the variance that there is in the real world. And there is a gap there, and there are many techniques to actually infuse your simulated data with this variation called domain adaptation, where essentially what you do is you have your simulator and you just create variance in every value that you have in the simulator. For example, I don't know, brightness or textures or stiffness of things, and in that way you try to overcome this, but it's not correct, for example, and that's when you don't have tactile sensing. Tactile sensing, because things are deformed, the gels that are on the sensors are deformed. It's really hard to modulate. And they're not good simulators so far. There are simulators, but they're very naive, and you cannot use them for complex tasks. And now that we have the compute to actually train behavior cloning models, it's actually easier to, or I hope it's going to be easier. It's been shown by other labs, and I'm about to explore it myself. It's going to be easier to actually set up a new task without pre-program it on the simulator, which is a big burden. And you just set everything up, you give a few demos, and then it learns to do the task. Okay. I mean, a recent paper I wrote an article about called Diffusion Policy. You just need 50 demonstrations, and you just do not self-supervised, you just do supervised learning. End to end, you have, this is what the observation of the robot was, this is what the action was from the demonstrator, learn to map it, and works well.
Okay. And out of curiosity, what kind of simulation environment do you use for...
For this work, we use Tactile Gen 2. There is also Tacto. These are the two dominant ones so far. But as you see, they're based on the naive simulators. That was... my brain's stuck. Yeah, never mind. It's a very naive simulator. The physics are okayish, but in terms of realism, the images are not even close enough.
Okay, I
to
was
do the
wondering
wheel.
if there was any gazebo or any.
No, we don't use gazebo because that's an interesting thing, because we wanted all the robots in the lab to be ROS2 enabled. So we actually spent a lot of time to teleoperate this robot with servoing. And actually nobody uses ROS2, especially for robot learning. There are Python APIs for all the robots, so you don't have to have all this hassle to do ROS, gazebo, whatever. Gazebo is not great too. It's computationally not efficient at all. And if you want to do, so Isaac Jim is very prominent right now, or I don't know what, they change their name quite often. It's very realistic, but still it's missing the tactile sensing.
Yeah, that's.
And now you have humanoids going on, and every humanoid robot has a different tactile sensing, vision-based, force-based. So it's really hard. Actually, one of the works I want to do for the foundation model is make it invariant to what kind of sensing, what kind of tactile sensor you're using to detect it.
Great. Okay. Any more questions? Last call. Okay. Thank you, Foti.
I don't know if somebody from the. I had the question.
No, I think it's just Professor Vissot, nobody else. That's it.
Okay. Thank you very much
again.